Hello students, welcome back. Let us resume our discussion in section 4. Previously, we studied some motivating example problems, which are basically the first-order homogeneous system of linear ODEs with constant coefficients. Now, if you have variable coefficients, then it's going to be a linear system, yes. It's going to be a first-order system, yes. But the method we are going to apply will not work very well. Some of them is going to be dealt with in lesson 15 as an optional part, but in general it's going to be hard. Here in this lesson 14, we are going to focus upon constant coefficient case. In other words, we are in this kind of situation where this matrix A is constant matrix, and the ODE or the system of ODE can be written as in this form, as I just highlighted in bold. In this case, we saw that this formula works, and this formula can be calculated if, and this may be big if, but in any case, it's if we can calculate the matrix exponential. In this particular case, we depended heavily upon log, so that's no good. We need better tool, and the better tool that we're going to discuss here is a Laplace transform method. And here is the grand conclusion. We can calculate the matrix exponential using the Laplace inversion because the Laplace transform of the matrix exponential turns out to be something like this, which we call a resolvent matrix. But then again, we have a problem. The Laplace transform, by the way, was defined in terms of integrals. Does everybody remember? The Laplace transform of f of t in real case is actually a function of s, and then it turns out that this is integral 0 to infinity and e to the negative st power f of t dt. That was the definition. So we need to do some calculus, but then again, this is a matrix function. So how do we handle the integrals of matrix function? That's something we have to discuss before coming back to this grand conclusion. So let's go ahead and do that. Calculus of matrix functions. Let's cover that, and then we can go over to the conclusion. Okay, let's begin. First, differentiation. The derivative of the matrix function we can simply find out by taking the derivative of each entry. Here's an example. This is a 2 by 2 matrix function, so we have to take the derivative 4 times for each entry. 1 for each entry. If you want to prove, well, here we go. We can form the Newton quotient for the matrix function. Here, I used 1 over h rather than divided by h because I wanted to emphasize that 1 over h is a scalar multiplication. Now here inside the bracket, this is just matrix addition subtraction, so it applies to each entry, so aij entry like that. And then this scalar multiplication applies again to each entry, so we have h in denominator like that. Consequently, we have the Newton quotient of each entry, so upon taking the limit, we get a derivative at each entry. That's a foolproof, actually. It's a one-liner. How about the integration? Similar, we can simply take the definite integral of each entry separately, apply the fundamental theorem of calculus 4 times, 1 for each entry, and that's it. Indefinite integral, I'll try not to use it very much because there's a bit of a problem. The proof, well, proof is again a one-liner. Please recall that the definite integral is defined through Riemann sum, and Riemann sum is basically the sum of those function values here times delta tk, the size of the intervals or the width of the rectangles. But here in this case, this delta tk, the width of the rectangles, that's scalar multiplication, so that applies to each entry. And as for the summation here, again that applies to each entry. So at each entry, we have Riemann sum. So upon taking the limit, delta t going down to 0, we get the definite integral at each entry. There goes the full proof. The hard part is the Riemann sum part. The proof part is not too bad, as a matter of fact. The matrix part is never too difficult. Next, Laplace transforms, and again, as expected, the Laplace transform of a matrix function is the Laplace transform at each entry. And to check this, please check page 123 in our textbook. That's where we have this standard Laplace table, and we had been consulting it, I don't know, maybe 100 times or something like that. We have been consulting the same page since chapter 2. If you're on proof, well, it goes like this. The Laplace transform is basically the integral of the matrix function, but the matrix function, you can apply all those integrals to each entry. So basically apply the Laplace transform to each entry, and that's about it. And then of course inverse transform is just precise backward process, no big deal there. Finally, let's talk about constant coefficient matrix. In short, I can take the constant coefficient outside of the derivative like this, or I can take the constant coefficient outside of the integral like that. But how do we actually prove it? Well, this is a derivative of a matrix function, which is scalar multiplication. F of t applies to each entry. So if you take the derivative, that is a derivative of each entry like that. But each entry is just one-dimensional function, and there aij is constant coefficient, so I can always pull it out, resulting that. Similar thing goes here. aij is constant coefficient at each entry, so take it outside of the integral like this, and then we get the same result as before. In case you were unable to follow, here are some examples. Calculate the scalar multiplication first, then you're going to get this matrix, and then take the derivative for each entry, so we get this. We have to do that 4 times, but in this case just 3 times because we have 0 here. Or we can take this entire matrix out and then apply the derivative to t squared only, getting t to t, and then take the scalar multiplication. Do we get the same answer? Of course. This is for the definite integral. Take the scalar multiplication first, getting this matrix function, and then apply the fundamental theorem of calculus to each entry. We have to do it 3 times, 1 for each entry, but this one is 0. Or we can take this entire matrix out and apply the definite integral only to scalar function like this. Applying the fundamental theorem of calculus, we get that, and then take the scalar multiplication afterward, we get the final expression. And is this the same as the final expression of the previous computation? The answer is yes. Please check. It's an easy check. By the way, what if I try to do the same thing with indefinite integrals? We have a problem here. Let's apply the scalar multiplication first and get this matrix, and then apply the antiderivative to each entry. So we have 4 integral computations. Consequently, we have 1, 2, 3, 4 integral constants, and they all come here. So we have arbitrary constant matrix C popping out here that consists of arbitrary entries. However, if we take this matrix out and apply the antiderivative to the scalar function, then we have only 1 integral constant. I already used up C, so let me use K here. And then we can apply the scalar multiplication. Then this is the matrix that follows, and you have only K. Here we have 4 arbitrary entries, C11, C12, C21, C22. They're different. And can we mend this problem? Well, most of the time it's going to be possible, but it's going to be cumbersome, and therefore the indefinite integrals are best avoided. I'm not going to use it in this chapter. In chapter 9, I'll always use definite integral, but no indefinite integral. For example, like this, we want to establish some integral formula for a matrix exponential, but instead of using antiderivative expression, I'm using the definite integral t is going from 0 to t like that. Excuse me, dummy variable is tau. Tau is going from 0 to t like that. And this one is, of course, more straightforward here. It's a derivative formula for the matrix exponential e to the at power. As expected, we have a times e to the t power, just like chain rule form. Now, how do you prove these? Oh, by the way, before proving it, let's consider an application first, especially the application of the first, which I just highlighted in blue. Let's begin with this. The formula for the solution formula for the first order homogeneous system of linear ODEs with constant coefficients. And then this is the same formula that you used right here in this motivation example problem here. You see, the same formula we used. Under this formula, it turns out that this y of t satisfies the ODE and also the IC. How does it work? Well, here's the proof. Take the derivative using this blue formula, which we have yet to prove, but we'll prove it a little bit later, so we can still use it. So take the derivative. Now, times y star, that's just constant coefficient, staying the same, no problem there. Basically, taking the derivative of this exponential, and as we're going to prove here, it's going to be this. Let me highlight those in blue. And then, please note that exponential times y star is nothing more than y, so we have ay. So, y prime is ay, we get the ODE, or the system of ODEs. How about the initial condition? That's just straightforward algebraic computation. Plug in t equal to 0, then y of 0 is a times 0. So a times 0, what do we have? We have 0 matrix. E to the 0 matrix is identity matrix I. So I times y star, we have y star. So y0 is y star. So we have the IC, and previously we saw y prime is ay, we have ODE. So this one is the correct solution formula. By the way, here's a remark. In general, if you have not y of 0 is y star, but y of t0 is y star, then we have a little bit more extended form, like this, a t minus t0. Well, you can consider it as horizontal shifting, as a matter of fact. Previously, we have just a times t, but t0 goes to a, 0, and then it's going to be just horizontal shifting. Okay, so much for the ODE and IC and the solution formula. And we saw that this formula is going to be needed. We didn't prove it yet, so let's go ahead and prove it. Here's the proof, but before proving, well, let's discuss the corresponding one-dimensional formula for real functions. Yes, this is just a straight-ahead chain rule. And for the second formula here for the antiderivative, it's nothing more than taking the antiderivative and plugging in top and plugging in bottom, subtracting one from the other, the fundamental theorem. And then here, if I multiply by a, then multiply by a, that's going to be killed, and that's going to be killed. And exactly the same thing as before. Okay, let's go ahead and prove the first formula here. And then let me see. Alright, here's the proof. we have the Taylor-Maclaurin series expansion of e to the at, and simply take the derivative term by term. I is going to be gone. At is going to become just a. And this t squared, it'll come out, and we have 2 over 2 factorial. So that's going to be gone. And then third power is come out, and then we have 3 over 3 factorial. So that's 1 over 2 factorial. Instead, we have second power. And fourth power, 4 will come out, and we have 4 over 4 factorial, resulting in 1 over 3 factorial. And subtracting 1 from the power, we get the third power. Just be careful and do your computation, you're going to get this. And then please note that a is common everywhere, so factor it out. And then what do we have here? I, at, 1 over 2 factorial, a squared, t squared, 1 over 3 factorial, a cubed, t cubed, and so on. This is nothing more than the same Taylor-Maclaurin series expansion that we started off with, e to the at power. So the conclusion, we have a times e to the at power. So that concludes the proof of this derivative formula for the matrix exponential, or the blue formula here. All good? Okay, now let's go to the green formula, which is quite a bit less important compared with that green, but here we go anyway. Alright, this is just Taylor series expansion here. So, same Taylor-Maclaurin expansion of e to the a tau, and then take the antiderivative term by term, we're going to get the first line. No sweat, just add 1 to the power and divide, add 1 to the power and divide, add 1 to the power and divide, just continuing here. We start from 1, but add 1, so t squared, and divide, so we have 1/2. But 1/2 versus 1 over 2 factorial, they're the same, because 2 factorial is 2 times 1, no difference. How about this one here? Add 1 to the power, so 3, and then divide, so we have 1 over 3 times 2 factorial. 3 times 2 factorial, that's 3 factorial, so we have 1 over 3 factorial. Same goes here. Add 1, fourth power, and divide, we get 4 factorial, and so forth. And then if you plug in the top and plug in the bottom, subtract 1 from the other, plug in t, then all the taus will become t, and subtract 0, because plug in tau equals to 0 or 0, no change there, and break up the parentheses, no problem there. So far so good, right? Now what do we do here? Does it resemble anything? You see, we did this plug in t, plug in 0, subtract 1 from the other, and multiplication by a was there before, so yeah, we got all these. And then now what? Does this resemble something? 1 over 2 factorial squared, 1 over 3 factorial cubed, 1 over 4 factorial, fourth power. This looks exactly like the Taylor-Maclaurin series expansion of the matrix exponential e to the at power, except that it did not begin from I. So what do? I just artificially add I and then subtract I to keep the balance. If I do that, this whole thing will become e to the at power. And then of course I have minus I there. So that's the conclusion of this proof. Okay, we have these two formulae here. This one is humongously important, and then we just used it here as well. This one, I don't know. I don't know if this is going to be any useful, but here it is anyway. It's kind of parallel. We discussed the derivative formula, so why not antiderivative formula? So I just put one and the other. And our textbook author did the same thing too, but I don't know whether this is going to be useful. Alright, let's stop here, and finally we are going to talk about the Laplace transform in the next video.